Before I go through the answers to the extra practice questions, I just want to take a minute to go over the exact values again and where they come from. Because we'll start with two special angles, 45 degrees and 60 degrees. And we consider these special because 45 degrees is what you get if you have a right isosceles triangle. So those two are the same size. So the rise and the run is the same. So I know that that angle is 45 degrees. Now, every right isosceles triangle is similar, meaning it doesn't matter what the lengths of the sides are, it'll still be 45 degrees. So we kind of go to lowest terms. I make it the smallest possible, so I'm going to say both of those sides are 1. So now using Pythagorean theorem, a squared plus b squared equals c squared. So 1 squared plus 1 squared equals c squared. 1 plus 1 equals c squared. 2 equals c squared, so c is the root of 2. So 1 root 2 is kind of the lowest form, the smallest right isosceles triangle. So now I can SOHCAHTOA this to know that the sine of 45 is 1 over root 2. Because SOH, S-O-H, says the sine of the angle is opposite over hypotenuse. The cos of 45 degrees is 1 over root 2 as well, because CAH, C-A-H, the cos of the angle is adjacent over hypotenuse, and the tan of 45 degrees equals 1 over 1, which is just really 1, because TOA, T-O-A, is opposite over adjacent. Now 60 degrees doesn't come from a right triangle to begin with. I'm going to start with an equilateral triangle. So pretend that that's equilateral and all of those sides are the same length. SOHCAHTOA only works with a right angle. But what I can do is cut this. Actually, I'm going to make a nicer diagram. A little bit nicer anyways. So what I can do is cut this in half and make a right triangle. So I'm going to ignore half of this triangle and just work with this half here. This angle will be 60 degrees, and now this angle up here, because I've cut 60 in half, is 30 degrees. So now we can add 30 degrees to our list of special angles. Now, I could make this equilateral triangle 1, 1, 1, but that's going to make it a little bit ugly when I cut it in half. So I'm going to start with the equilateral triangle having sides of 2, because now when I cut this one in half, it becomes 1, and I'm not dealing with decimals. If I would have made all the sides 1 and cut the bottom in half, it'd be 0.5 or 1/2, and I don't want to get into that. Now I'm going to look for this side here. Now this isn't the hypotenuse, so I'm using a squared equals c squared minus b squared. It's just the other form of Pythagorean theorem used when you're looking for a leg. So a squared is 2 squared minus 1 squared. C is the hypotenuse, so it's the 2. The other side is the 1. So a squared equals 4 minus 1. A squared equals 3. So a equals whatever the root of 3 is. So now I'm going to focus in on this triangle, and I actually like to redraw it for my students so that we don't have all the extraneous information. So that's 1, that's 2, and that is root 3. That's my 60 degrees, and that's my 30 degrees. So now I can do sine of 60, cos of 60, and tan of 60. And then I'll also be able to do sine of 30, cos of 30, tan of 30. And I'm just going to SOHCAHTOA the triangles, always looking at what angle I'm referencing. So for 60, sine is O over H, opposite over hypotenuse. So that's root 3 over 2. Cos is adjacent over hypotenuse, A over H, which is 1/2. And tan is opposite over adjacent, O over A, which is root 3 over 1, which is just the same as root 3. Now to do 30 degrees, I'm going to switch the angle I'm referencing, which means the hypotenuse will stay the same, but the O and the A actually trade spots. So sine of 30 is opposite over hypotenuse, 1 over 2. Cos of 30 is adjacent over hypotenuse, root 3 over 2. And tan of 30 is 1 over root 3. Now, these 9 values for 45, 60, and 30, some people will say you have to memorize. I don't have my students memorize them. I have them memorize these two triangles and draw these two triangles on the top of the page whenever they're working with exact or precise values and go from there. Because the key is exact or precise values means you're not allowed to touch your calculator. If you type in cos of 45, you are going to get a non-repeating, non-terminating decimal, which you'll have to round, and your answer will be inexact. 1 over root 2 is an exact answer. So when I tell students to give the exact answer and they give me a decimal, then it's an automatic 0. So we are going to find the exact or precise value of the following. So again, as soon as I see the words exact or precise, I just quickly sketch those two triangles. 1, 1, root 2, and I know that's 45, and 2, 1, root 3, that's 60, that's 30, because whenever you're working with exact values, that's what you need to know, and I can pull anything off of there. So sine of negative 45 is a little bit different, because now we're going back to our understanding of angles that has them as rotations on the xy plane. So negative 45 degrees is going to be down there. So negative 45 really rotates around to there. Negative 45 is coterminal to 315 degrees. Don't really need to know that, but I wanted to go over that the same. So if that's 45 degrees, then it's this triangle that it's placed there. So that's root 2, because the hypotenuse is always root 2. This triangle has actually been kind of rotated around to go there. That's a 1, and that's a 1, because the legs around the 90 degree are always 1. 1 and 1. Now I look and say, okay, because of where that is situated, do I have to add any negatives? That's to the right 1, so it's positive. But this here is down 1, so it's negative 1. So now to find the sine of 45, I'm just taking O and H out of this triangle. Opposite is negative 1, hypotenuse is root 2. So the sine of negative 45 is negative 1 over root 2. Tan of 150. So again, I'm going to start by sketching where 150 degrees would be. There's 90, so it'd be another 60. So that ends up being 30 degrees if that's 150 degrees. So in this case, I'm working with my 2, 1, root 3 triangle. And this is the one you have to be careful, because with the 45, the legs are always 1 and 1, so you don't have to worry about getting them in the right location. For 30 and 60, the legs kind of change how they're related to the angle. So I need to get this information onto here in the right order. The 2 is the easy one. It's always the hypotenuse. Now, root 3 is touching the 30 degrees. Since the 30 degrees is down there, that means that's root 3. The 1 is opposite the 30, so the 1 has to go there. After I insert my triangle in the right place, then I say, do I have to add in any negatives? The hypotenuse is never negative. This 1 is up, so it's positive, but this root 3 is backwards or to the left, so it has to be a negative. So now tan, TOA, comes from this triangle, opposite over adjacent, and then a lot of the times you'll see the negative moved to the top of the fraction. So 1 over negative root 3 is the same as 1 over negative 1 over root 3. Cos of 300. So if I rotate around 300 degrees, that leaves me 60 inside the triangle, because I'm short 60 degrees from a full revolution. So again, that's this triangle that I have memorized. 2, 1, root 3, 60 degrees is there, so I have to make sure I get everything in the right spot. 2 is always the hypotenuse. Opposite the 60 is root 3. Adjacent or touching the 60 is 1. I look at the triangle and say, because this is going down, I have to make my root 3 negative. Now, you always draw your triangles up or down to the x-axis. Never join them up sideways. It's just convention. That's the way it's done. But now, cos of 300, the negative never really comes into play because I'm doing adjacent over hypotenuse, which is 1/2. Prove that the sine of negative 300 is the same as the sine of 60. So I'm going to say, okay, with the left side, I'm going to work with the sine of negative 300 and figure out what it is. And for my right side, I'm going to figure out the sine of 60. So 60 is just a normal rotation in quadrant 1. And again, this is the triangle I want, 2, 1, root 3. My 60 is in the bottom corner. So that's going to be 2, root 3, 1. Everything is positive. So this equals root 3 over 2. Opposite over adjacent. Negative 300 degrees is going to wind up there. So that'll be 60 because negative 300 is 60 degrees short of a full backwards revolution. So 2 root 3, 1, nothing is negative, so that equals root 3 over 2. Therefore, left side is the same as the right side, and I've proven that the sine of negative 300 degrees is equal to the sine of 60 degrees. For 30 degrees, show that tan t equals sine t over cos t. So 30 degrees is my 2, 1, root 3 triangle, and my 30 degrees is in the upper corner. I'm going to put it on the quadrant. I don't really need to because 30 degrees is just less than 90, but I'll put it on here anyways. 2 is the hypotenuse. 1 is across or opposite. Root 3 is the adjacent. Everything is positive because of the location. So now tan of t becomes opposite over adjacent, 1 over root 3. Sine of t over cos of t becomes sine of t is 1 over 2, opposite over hypotenuse. So that's sine t over, because of this middle line, cos t is root 3 over 2. This line there really means to divide, and I don't particularly like to have fractions over fractions, so I'm going to change that just to a straight division. Instead of going 1/2 over root 3 over 2, I'm going to do 1/2 divided by root 3 over 2. To divide by fractions, you flip and multiply. So I don't flip the first one, I flip what I'm dividing by. So since I'm dividing by root 3 over 2, it becomes 2 over root 3, and it changes to multiplication. Multiplying by 2 and dividing by 2, we have a 2 on top and bottom, we can cancel. So I end up with 1 over root 3. So therefore, tan of t equals sine of t over cos of t, because we got the same answer for both. Now, I didn't do left side, right side for this. You could have said this is the left side, this is the right side, therefore left side equals right side. But the instructions are to show. And show is just a little bit less formal than a proof. A proof, you really have to be aware of your form. Show just means, oh look, I showed that the answers were the same. Now we're going to solve for t in between 0 and 360 degrees and figure out root 2 sine t minus 1 equals 0. What angles for t will make this work? First thing I'm going to do is solve it like a normal equation. So I'm going to bring the 1 over and add it or make it positive. 0 plus 1 is 1. Then the root 2 is dividing my angle. Sorry, the root 2 is multiplying the sine t, so I'm going to divide it. So now I want to know what angles have a sine of 1 over root 2. Hopefully 1 over root 2 kind of rings a bell. It's back to our 45-degree triangle. Now, this is where cast rule, which was talked about earlier in the content, comes in handy. So cast is C-A-S-T, and it tells us which values are positive. So all of them are positive here, and sine is positive here. For our question, sine is positive. So that means my triangle could be in quadrant 1, or it could be in quadrant 2. 1, 1, root 2, 1, 1, root 2. So I know this is 45. So one answer for t is 45 degrees. To get the other answer, though, I have to think about what would I have to rotate around to get to this line. It's 45 degrees inside the triangle, but I already have 45 degrees as an angle. If I just say 45, I'm talking about this one again. This is a different answer. But this line here is 180 degrees. So to rotate here, it's 180 degrees except for 45. So my other answer is 135 degrees. And now the reason they have to say within one revolution or between 0 and 360 is I could keep going on forever. I could say, well, 45 is an answer. So is 405 degrees. rotate all the way around, and add 45. And I could keep doing that and generating multiple answers. So this locks us in that we only have to find answers on one revolution or one circle. For the last example, I have tan of t equals -1 over root 3, and it looks a little bit different or weird because of how I had to type it in, but that's really what I have. Now, hopefully 1 over root 3 makes you think of this triangle, and tan is TOA, opposite over adjacent, so it has something to do with my 30 degrees. I'm going to go to cast rule to figure out where this could be. So this tells me where they are positive. So tan is positive in the A, where they all are, and positive down here. Well, in this case, tan is equaling a negative. So it means that I'm either here or sine is positive here. By default, that means cos and tan are both negative, and cosine is positive here. So by default, sine and tan are both negative. So that tells me to draw my triangles in quadrant 2 or quadrant 4. Now, the hypotenuse is always 2 because it was tan was 1 over root 3. Opposite has to be 1, so the 1 goes there and there. And root 3 has to be the adjacent. I'm going to add in my negatives where they go, and there are my two triangles. So now I know that that's 30 degrees and that's 30 degrees. So to get my answers for t, I'm figuring out what rotations would land me there. So this first rotation is all the way to 180, but for the 30 degrees inside the triangle. So my first t is 150 degrees. This second option goes all the way around here, so it's almost at 360 except for the 30 degrees inside the triangle. So the other answer is 330 degrees.